So we have a position vector r that will depend on some parameter, which I will call s. You'll see why very soon, in such a way that the derivative is this given unit vector u hat. So why do I use s for my parameter rather than t? Well, it's a convention. I'm moving at unit speed along this line. So that means that actually I'm parameterizing things by the distance that I've traveled along the curve, along this line. So here it's called s in the sense of, arc length. Or actually it's not really an arc because it's a straight line. So it's the distance along the line. Okay, so because we are parameterizing by distance, we're just using s as a convention, just to distinguish it with, distinguish this from other situations. And so now the question will be, what is dw ds? What's the rate of change of w when I move like that? Well, of course, we know the answer because that's a special case of a chain rule. So that's how we will actually compute it. But in terms of what it means, it really means we are asking ourselves, we start at a point and we change the variables in a certain direction, which is not necessarily the x or the y direction, but really any direction. And then what's the derivative in that direction? Okay? Does that make sense as a concept? Kind of. I see some faces that are not completely convinced, so maybe I should show more pictures. Well, let me first write down a bit more and show you something. So I just want to give you the actual definition. So first of all, in case you wonder what this is all about. So let's say that the components of our unit vector are two numbers a and b. Okay? Then it means that we'll move along the line x of s equals some initial value, the point where we're actually looking at the directional derivative, plus s times a. Maybe I should say plus a times s. And y of s equals y0 plus b times s. And then we plug that into w. And then we take the derivative. So we have a notation for that, which is going to be dw ds with a subscript in the direction of u to indicate, in which direction we're actually going to move. And that's the directional derivative. In the direction of u. Okay, so let's see what it means geometrically. Oops. So remember, we've seen things about partial derivatives, and we've seen that the partial derivatives are the slopes of slices of the graph by vertical planes that are parallel to the x or the y directions. Okay, so if I have a point, at any point I can slice the graph of my function by two planes, one that's going along the x, one along the y direction, and then I can look at the slices of the graph. Let me see if I can use that thing. So we can look at the slices of the graph, they're drawn here, and then we look at the tangent lines to these slices, and we look at their slope, and that gives us the partial derivatives, in case you're on that side. we want to see also the pointer, then it's here. Okay. So now, similarly, the directional derivative means actually will be slicing our graph by a vertical plane. It's not really colorful. It's something more colorful. We'll be slicing things by a plane that is now in the direction of this vector u, and we'll be looking at the slope of the slice of the graph. So what that looks like here, so that's the same applet, by the way, that you've used on your problem set, in case you're wondering. So now I'm picking a point on the contour plot, and at that point, I slice the graph. So here I'm starting by slicing in the direction of the x-axis. So in fact, what I'm measuring here by the slope of this slice is the partial in the x direction. It's really partial f partial x, which is also the directional derivative in the direction of x, of I, sorry. And now if I rotate the slice, then I have all of these planes. So you see at the bottom left, I have the direction in which I'm going. There's this like rotating line that tells you in which direction I'm going to be moving. And for each direction, I have a plane. And when I slice by that plane, I will get, so I have this direction here going maybe to the southwest. So that gives me a slice of my graph by a vertical plane. And the slice has a certain slope. And the slope is going to be the directional derivative in that direction. OK? I think that's as graphic as I can get. OK. Any questions about that? No? OK, so let's see how we compute that guy. So let me just write again, just in case you want to. In case you didn't hear me, it's the slope of the slice of the graph by a vertical plane that contains the given direction u, that's parallel to the direction u. So how do we compute it? Well, we can use the chain rule. The chain rule implies that dw by ds is actually the gradient of w dot product with the velocity vector dr ds. But remember, we said that we are going to be moving at unit speed in the direction of u. So in fact, that's just gradient w dot product with the unit vector u.